The most common measure of average, the arithmetic mean, is one of the most ubiquitous and useful technologies ever developed. Wait, you don't think of the average as being a technology? Hi, and welcome back to the Data Science Rabbit Hole. You probably think of facial recognition algorithms as technology, and natural language processing algorithms and encryption algorithms. There are lots of mathematical innovations that we consider to be inventions or technology, even though they're not some kind of physical device. The arithmetic mean is one of the most useful and ubiquitous technologies ever developed. But like the wheel, it's so simple that you come to understand it in childhood. Still, it was revolutionary in its day, and it's used in countless applications today, from calculating your high school GPA to predicting the weather. When I ask my students if the mean is the best measure of average, I often hear them defend it as a no-brainer. But here's the thing. The mean is not some innate mathematical truth that's obvious and has been around forever. It's a relatively new invention that had to be discovered and developed over time. In fact, for centuries, many of the greatest mathematical and scientific minds struggled with the concept of the mean. They knew something was missing, but they couldn't quite grasp its power and potential. It's like they were trying to find the right key to unlock a door, but they were so bad at it that they made locksmiths everywhere feel like they had job security. So let's go spelunking into the history of the arithmetic mean. Get your hard hats and headlamps ready, because this rabbit hole goes deep. Ancient Greece, home to philosophers, mathematicians, and some of the earliest attempts at using averages. Thucydides, in his History of the Peloponnesian War, written in the late 5th century BC, cites Homer's account of Boeotian ships and the ships of Philoctetes, which had 120 and 50 men respectively. Thucydides reasoned that Homer only specified the largest and smallest because they were the most notable, and then he used the mid-range, the mean of the lowest and highest values, to conclude that this particular armed force was relatively small. But wait, there's more! Thucydides also tells of the Phaeacians, who counted the bricks on an exposed area of a city wall to estimate its height before building siege ladders. The soldiers counted the bricks multiple times, and all the counts were recorded. Then the count that came up most frequently, what we now call the mode, was chosen as the best estimate. Pretty savvy, right? The Pythagoreans, known internationally for their amazing work on right triangles, also had a concept of the arithmetic mean, first mentioned in the work of Archytas, not long after the time of Thucydides. The Pythagoreans defined the arithmetic mean in terms of the equation of differences, such that if a plus b equals c minus b, then b was the mean of a and c. Of course, they knew that b could be calculated as half the sum of a and c, but their official version was more about a mathematical relationship between two numbers and a third, rather than a practical tool for dealing with large sets of data. Nevertheless, their ideas laid the foundation for the modern ideas around the arithmetic mean. Now, as it turns out, many of the earliest mathematical minds were also stargazers. The Babylonians, for instance, seem to have an inkling of averaging multiple observations, though their precise method has been lost to time. And in Greece, Hipparchus in the 2nd century BC toyed with the idea of the arithmetic mean in his astronomical work, but it wasn't exactly catching on like wildfire. Perhaps they were too busy gazing at the stars to fully appreciate the power of averages. Who knows? Here's a story from India, written down in about the 4th century AD, but likely much older, about a gambling king named Nala, who lost his entire kingdom in a dice game. To win back his riches, Nala sought out another king, Rituparna, who was known for his mathematical prowess. But how did Rituparna prove his skill? By counting the leaves and fruits on a single twig from a tree, and using that information to estimate the numbers of leaves and fruits on the two largest branches of the tree. Nala was impressed, but he spent the whole night counting to verify Rituparna's estimate, which was close, although not exact. This ancient tale demonstrates some understanding of the idea of representativeness that we now associate with the arithmetic mean. It also showed that they had an understanding that there was some kind of science behind what was going on with dice, and that there was some kind of a connection between the math that you'd use to look at dice and the math that you'd use to estimate the number of leaves and fruit on a tree. But still, we haven't quite got to the point of inventing the arithmetic mean. Maybe people this far back in history were too busy fighting wars and inventing fancy hats to spend too much time with the math. But in the 16th century, somebody finally stepped up. That someone was Jacob Kerbel, whose book Geometric featured a diagram that's like a primitive version of social media for feet. You see, Kerbel knew that if you relied on just one person's foot to measure something in feet, you could wind up being a bit off. So he rounded up 16 dudes with different foot sizes, using a mix of feet to define a unit of measurement called a rod. And thus, the mean was born. Well, not quite. Again, it's an implicit use of the concept. But at least we just took a step forward. The 16th century, when people were finally getting the hang of this whole arithmetic mean thing. Astronomers in particular found it quite handy for getting better estimates of the celestial bodies they were observing. But let's not get too excited just yet. While earlier observations may have hinted at the use of the mean, it wasn't until the late 1500s that astronomers started explicitly mentioning it. Perceiving under impulse power only. Let's talk about the great astronomer Tycho Brahe. He knew that combining observations of the same quantity, like a location of a star, would give a better estimate. But he had a strict rule. He only averaged measurements taken with the same method. So if you tried to sneak in a measurement taken with a different approach, he would separate it like a disappointed parent separating fighting children. But astronomy wasn't just a bunch of academics looking through telescopes, it had practical application. Ships needed to know the difference between the north we see on the map and the magnetic north shown on the compass. In the 1600s, navigators at sea started using the mean of several observations to measure magnetic declination. In 1722, the late Roger Coates published a posthumous work. Well, I guess he didn't publish it, but someone published it for him, posthumously, because he was dead. Anyway, it would make any high school physics teacher proud. He pointed out that the mean is like the balance point of a seesaw, where the data points are like the kids sitting on it. And we all know what happens when one side of the seesaw has more kids than the other. Chaos ensues. So let us thank Coates for showing us the importance of balance in our data. Fast forwarding to 1755, we meet Thomas Simpson, a math professor who started his career by lecturing in coffee houses, which was apparently quite the trend back then. In a letter to the president of the Royal Society, Simpson noted that not everyone was sold on the idea of using the mean, as some, quote, persons of considerable note, quote, argued that a single observation taken carefully was just as reliable as the mean of many. But Simpson was not deterred. He proved mathematically that the arithmetic mean, when applied to multiple observations, would have an error less than some certain number, he called it m, divided by the number of observations. In other words, you could reduce the maximum possible error in your measurements by simply taking more observations. So the use of the mean was becoming more common in the mid-18th century, although it wasn't yet embraced by everyone. In 1777, Daniel Bernoulli wrote about taking the mean of several observations, calling it a universally accepted rule, except that it wasn't. Even Bernoulli himself was skeptical, questioning whether all observations were equally prone to error. Bernoulli wondered if it was fair to assume that errors of just a few degrees might be equally likely as errors of a few minutes. He felt that you should just average the good observations and toss out the bad observations. Of course, he never specified how to tell what's a good observation from a bad observation. So even in the late 1700s, we're not quite there. In 1809, the prince of mathematicians, Carl Friedrich Gauss, noted that taking the mean of several equally good observations had become customary by that time. It's important to note that at this point, the arithmetic mean was simply seen as a way of taking multiple observations of the same physical quantity and combining those observations to get a more precise estimate. This isn't quite the same as the way we look at the mean today, but it is a big step forward. By the mid-1800s, significant progress had been made thinking about the mean, as evidenced by the work of Adolphe Quetelet and his studies of the average man. During this time, there was a rise in mentions of the average height of adult men, the average weight, and other similar concepts. Despite the progress, Quetelet still saw the average as an estimate of the underlying parameter. For instance, the height or weight of some platonic form of the average man, which served as a theoretical mold from which all the rest of us are just imperfect copies varying from the specifications. William Stanley Jevons made an important distinction between the terms mean and average. He believed that the former should refer to multiple observations trying to estimate a static quantity, while the latter should be used for the arithmetic mean of a set of different things, such as people's heights, which he considered a, quote, fictitious mean, unquote. Before Jevons, saying that the average family had 2.4 children would have sounded absurd because obviously you can't have a fractional child. But Jevons' idea of the fictitious mean had finally taken root, and it allowed the mean to take on values that the actual observations never could have. Jevons recognized that all measurements of continuous quantities could only be approximately true. Where this assertion doubted, he wrote, it could readily be proved by direct experience, for if any person, using an instrument of the greatest precision, makes and registers successive observations in an unbiased manner, it will almost invariably be found that the results differ from each other. Therefore, he considered the existence of error in all measurements as the norm. Despite representing no truly existing quantity, the average, when employed as the fictitious mean, was of the utmost scientific importance. It allowed us to conceive a multitude of complex details in a single result, and to make a hypothetical simplification of a problem, avoiding complexity without committing error. Jevons compared this idea to Archimedes' concept of representing a physical body by its center of gravity, as suggested by Coates in 1722. In the late 19th century, some folks in the math and science community were all about the median. They claimed it was easier to calculate than the arithmetic mean. And they weren't wrong. Without access to digital computers, crunching a bunch of numbers is no joke. Others like the median because it's less sensitive to outliers, and outliers can really throw off your average. And believe it or not, some of them thought the median was easier to understand. Can you believe it? Well, sure, it's all relative. What did your elementary school teacher teach you? Over time, the true believers in the median started losing ground. As statistical theory developed in the early 20th century, the mean's connection to important concepts like squared error, the Gaussian or normal distribution, and expected value brought the mean at last to the supremacy that we see today. So listen up. You might think of the arithmetic mean, or as you so casually call it, the average, is just some run-of-the-mill statistical tool. But this is a revolutionary innovation in statistics and for science. So please don't underestimate its importance. Well, that is all for today's spelunking adventure down the rabbit hole. I hope you enjoyed this. If you did, consider subscribing, hitting the like button, doing whatever. Meanwhile, I'll see you when I see you.